Okay, so welcome everybody to this AJS seminar. Today's speaker is Jose Raul Martinez. I will remind everybody this seminar will be recorded. And the title of this seminar is KratosMultiphysics and local reduced order models.
Thank you. Well, morning. Yeah, good afternoon, everybody. Thank you for the invitation. And well, I come from the University, Polytechnic University of Catalonia, Barcelona Tech, and I work in the KratosMultiphysics group. And here I am now in CISA in a cooperation that we have in a European project. And I wanted to talk a little bit about my group, the KratosMultiphysics. So that's why I want to first introduce Kratos, and then we'll talk a little bit about how I implemented the Galerkin POD within our software, and finally what some of the current work that we are doing here in local reduced order models. So this is pretty much the content, the three topics that I want to talk. What is Kratos, the ROM application in Kratos, and then local ROMs. So first I will present Kratos very generally, and this is really my honor because, as you will see, this is very long work for many people. Many people have been involved, and I want to start giving you a historic development of the code, and then what it can do now. So let's get started. So what is Kratos? And sure enough, if you just Google Kratos, you will get this, right? And so you need to find KratosMultiphysics. But what is Kratos? Okay, this is a framework for development of multiphysics solutions, which should be flexible and extensible, modular and scalable. And this is not really what Kratos is, but Kratos is supposed to be. And it's because it is, I mean, this is a guidelines that were in the mind of the father of Kratos. And when he really started, he had these three guidelines in mind, and we have tried to follow them. So this started in 2001, and here it is. So this is the original team, and the really founders, Xavi Royo and Puyan Datband, who in Barcelona started with these three guidelines that I mentioned before. And this is the first design by Professor Eugenio Oñate. I mean, he approved it. So they tried to split the tasks in this way so that these three guidelines that I mentioned before could be achieved. And the first license was a LGPL license. So it was very free, but not fully free. That's how it started. They started working on it, and it took a little bit of time. Until 2003 already, they had structural fluid, electromagnetics, and thermal applications. And they could do these kind of 2D bubbles in 2003. And then they had this in a CD-ROM, the first versions of Kratos, right? So this is the date, and it's working already. And it was working, but it was too complex, and it was very slow, as they tell me. So there were pointers pointing onto other pointers, and it was very difficult to understand, and also it was not very efficient. Everything was linked together. So what they did is, okay, this was version 0. What they did is, okay, let's refactor it, and let's split it. So now you have the core, the Kratos core, and then you have the applications separately. And then you can have apps, for example, the fluid structure interaction that depends, of course, on the fluid and in the structural application. Okay, increasing the performance, separating applications from the core, reducing implementation complexities, and creating the Python interface. Now the scripting is in Python. Python is going to orchestrate, but the code is going to be implemented in C++ for more efficiency. I have had the chance to check this code from 2004, 2005, and the essence is already there. So what you see there is pretty much the same structure that you can see now. So this was kind of, let's say, a good decision. At least it has been successful up until now. So they started working on the high performance computing, right? So the third of the guidelines that I mentioned. So MPI parallelization, and then this university, Ruhr Universität Bochum in Germany, they started also working with Kratos, and here they have a simulation of a tunneling machine. So this was very large simulation, and they used this MPI parallelization. Okay, they continued working, developing, and then 2011. So now I give a little bit of a jump on 2011, and then the team is growing. So here, the father of Kratos, Puyan Datband, Ricardo Rossi, Antonio Arese, who is now in University of Padova, Pavel Rushikov. But the team starts growing in Barcelona, but also Technical University of Munich joins, in particular the static chair. And up until now, the Technical University of Munich has been a very important partner within the Kratos group. So they have developed a lot of applications on their own. Now the code starts being more powerful, 100 million elements, and then it's scalable up until 1,000 cores, and it's 2011, right? So then the code now can solve problems of 400 million elements, and now we have this simulation of flow over the city of Barcelona. You can see here the Sagrada Familia, and the code changes the license. Now it's completely open. Now it's a BSD license. Now anyone can change it. Anyone can use it even for commercial purposes, and they don't even need to tell us. It's fully free. So now wind simulations create structure interaction in these inflatable structures, and they start working on casting. This is the click to cast, which is based on Kratos, and up until now it's successful. It's free, but then okay, with this opening of the license, some changes come. For example, this click to cast was bought by Altair. So now Altair owns this click to cast, and it's well, since they develop it privately now. And then Siemens and Airbus start using Kratos as research and the development framework. And okay, in 2017. There's many other applications like the multi-scale application, the isogeometric analysis application. And then since the team starts growing, many applications, many things happening, so they changed to GitHub. They had a different repository. Now they have GitHub, everything is open, everything is there, and start working on how to testing and improvement of the working as a community. 2019, and this is the last step that I'm showing here, is the Chimera application developed at Technical University of Munich. Altair creates this product, which is the inspired mold, which is based on Kratos. And another one, for example, the cost simulation application. Now Kratos can interact with other solvers via some kind of communication, some protocol, and then you can use Kratos with another software with this cost simulation application. Also in 2019, I joined at the end of 2019 for starting implemented the reducer model application. But before going into how I did it, I just want to show you some of the capabilities of Kratos. For example, yes, structural mechanics, they have solid elements and also axisymmetric, membranes, shell structural elements, linear, non-linear, and elastoplastic and damage. And I have here some examples of civil engineering and mechanical engineering. Also, for the fluid dynamics application, they have stabilized finite elements. So Kratos is historically more into finite elements, the finite volumes or types of discretizations. Reynolds average, we have these deforming of the domains using arbitrary Lagrangian Eulerian element formulations, and also these embedded methods. So basically, the domain is not defined up to a geometry really, but the elements can be cut with this. But you don't need to clean up. Not much cleanup is needed, right? So this is already in the CFDA application. Some other examples that I can show, some particle methods, and these ones are the discrete element method and the particle finite element method. Here I have some examples of pharmaceutical, some agricultural, some civil engineering applications. And hydraulics examples, for example, these gated spillways and this steel embassing, and the simulations made in Madrid and in the Flumen Institute, also there in Barcelona. Biomedical examples, so the simulations by Edu Souda, where basically you scan and you get your model, and then you do the simulations on this, on these models. I can move. Oops. Okay. Oops. This is the volume. Kratos also has this pre and post processor. This is also developed in Barcelona. It's called GIV. So we have this interface for creating the model, for meshing it, and of course, once the simulation runs, as you see with Kratos, and now it is running there, and fast forward. But once it finishes, you can also check the results in GIV, which is, well, it's not part of Kratos, but it has been very vinculated with Kratos, since it's also developed at in Barcelona, in the research center. So that's one way of very user-friendly. And of course, now the Kratos repository, you can, the version is 9.0. And if you just go to the repository, you can see it's basically C++ with a Python interface. So we have many applications. You go to the applications, you see there are many applications now being developed in Barcelona, mainly in the Technical University of Munich, but also Padova and other universities. And we're also open for these cooperations. So that's basically Kratos. Now you know it's been developed for 20 years, and it's very large framework for doing numerical multiphysics simulations. And now how I implemented the reusable model application in Kratos. So I wanted to use this as much as possible. So basically, and this is the same workflow that anyone would use if they wanted this to happen. So that you have a new idea, you want to be able to basically use most of the existing parts of Kratos. So of course, I wanted to be within the principles of Kratos. I needed to be flexible, scalable. So basically, for extensibility modularity, we are working on the residual. So we are not going to be very invasive. We are going to be using the residual so that we can basically, with the same implementation, that's the idea, use fluids and structures, structural elements, and also scalability. Since we want to orchestrate our training campaigns and also solve large numerical algebra in parallel, using either these library ROMs, which is developed at the Barcelona Supercomputing Center, or Dask, or any other library that exists, using, of course, the Python interface of Kratos. So just very quickly, what the POD, we have this residual formulation and our vector state, which depends also in the parameters vector. And this lives in this solution manifold, which is nothing but a set of all solutions for all parameters. So in POD, we assume this kind of approximation, linear approximation. And so if this is true, then we can project our residual in this way. And what is phi? Phi, of course, we know it's but in this case, this solution, the snapshot matrix for m parameters vectors. We take the singular value decomposition of that and we truncate it. And that is the optimal basis. But we know, of course, this term here is still high dimensional, and we want to hyper-reduce it. And the way we hyper-reduce, I think, over here, probably you use the empirical interpolation method, or it's discrete variant, but we use this empirical cubature method, which basically says, okay, since we're working in finite elements, right? So we have number of elements, and then we have this expression that I showed before, so the projected residual. And this term in the middle, this is very large, so we want to make it cheap. But in finite elements, what we do is actually doing this sum over all the elements of the projection, the sum of all the elements of the projection. And this L is nothing but the Boolean operator localizing the degrees of freedom of element E to this capital N. So that's what we do. We need to do a loop of the elements and then add the contributions. What we want to do is not visit every element. What we want to do is only visit elements in a subset and multiply by some weights. So that's what we need. We need this set of elements and the weights. And the way we do it is, okay, let me collect all of these terms for element 1 up until element number of elements. And also for all of the parameters. In this case, there are m parameters. Of course, this calligraphic R matrix would be number of elements by number of modes. And then if we stack many of these R calligraphic R's for parameter 1 up until parameter m, then we will get another snapshot matrix, but snapshots of projected residuals, which dimensions number of elements by modes by number of scenarios. So this matrix can be huge. And also that's why we also need these libraries for parallelizing. This computation might be very, very expensive, at least in terms of memory. But if we take the SVD of this, and then we get this basis, which is the basis of the residuals projected, we can solve this optimization problem, which says, okay, basically it's saying this exact same thing. So I want to find this subset and these weights such that I can add all of the, I can approximate all of the terms here. And this is the empirical cubator method, with some restriction that the weights need to be positive. Okay, that's it. That's what we do. And now that we have the elements and weights in Kratos, this is a typical loop. So I just loop over the elements and take their contributions to the left-hand side, to the right-hand side, assemble it, and solve for an incremental. And I check if I'm within tolerance, and if not, I repeat. That's Kratos. That does it for any simulation. What I did is, of course, I only add that this loop should not be done over all elements, but only over these selected elements. I multiplied, rather than assembling, just add, but add the contribution projected and multiply by the weight. And of course, Kratos doesn't know it's solving a reducer model, so I need to project it back to the full dimensional system. And I need to do some tricks so that not every element is really updated to make it cheap. So when that is done, that's it. We just plug this into Kratos. And is it working? Okay. For example, here is one parameter. This is only one parameter, which is the pressure on the face of this the Stanford bunny. And you can solve it in real time, even though it has like 50,000 elements, the regional system. This is, of course, quasi-static. And the goal of this, at least some of the applications that we have been using, for example, I can just put it in these small computers in a kind of digital twin fashion. So we put it in this small computer. In this computer, the Raspberry Pi 4 already has Kratos there. It's compiled. And then we are running the simulation in this small computer. And then we can see the results in this case for a turbine blade in real time. Okay, that's very nice, but this is already standard or classical methods. What I wanted to do now is extend the method of, in this case, going to local reducer models. And what is local reducer models? Basically, rather than having this, I mean, one single subspace, I will have many subspaces. And accordingly, I will have to use the best one. So I will move in the solution manifold, and I will use the best subspace, either the green one, the blue one in this image. Some questions now. When should one use local ROM? Of course, for problems where exhibiting slowly decaying Kolmogorov n widths, right? So the Kolmogorov n width, just to remember this, is the infimum of this space, because the space considered of the supremum over all of the members in the manifold, the solution manifold, and the infimum of the members of the subspace, and the u minus v in the norm by the inner product in this subspace. Basically saying the worst projection error in the best linear subspace. So this quantity, it depends, of course, in the problem, depends on the manifold. And if it's large, it means basically that, and if it's large, and if by increasing n, it doesn't decrease very fast, it means basically that our problem is not reducible. So what we need to do in these cases, local ROM is not the answer, but one of the alternatives. Of course, you can go fully non-intrusive. You can do some interpolations. You can do even nonlinear methods, like the ones that are, I don't know, the autoencoders, for example. But what advantages does this method have in comparison? Well, let's say it is built on top of an existing projection-based ROM. So let's say it's straightforward to implement. If you already have a projection-based ROM, you can implement this with not much difficulties. It's physics-based, and this is not an interpolation method, which you could use, of course. And the HROM that you use for the ROM galerting is still you can use it. I mean, as is. You can probably change it in order to improve it a little bit. But these are some of the arguments to use this method. Also, if your system, you know it's local, you know your system, you know your problem, and you say, by changing the parameters, I will remain within one region. So maybe you can also use this one. Okay, now, more practically, how to do it. Yeah, this is the steps, how to build multiple bases. Basically, you have your snapshot matrix, you split it with some algorithm. And then once you have the clustered snapshots, you just take the single value decomposition, and that's it, you get your bases. How to split it? The classical technique when you need to do clustering, of course, is k-means. When you have m snapshots and you need k clusters, basically the centroids, you need to assign k centroids to these M snapshots and assignment variables. Basically, this is the optimization problem. You need to minimize the distance from the centroids to each snapshots. So each snapshot can belong only to one of the clusters. And to solve this is via alternating minimization. So you randomly set your centroids, assign the snapshots, and recalculate them as the means. That's why the k-means. And then you just iterate until you converge. Well, that's it. But is it the only one? Maybe, of course, you have heard of other clustering techniques. I don't know, like spectral clustering, for example. But in order to use them for this, probably another more effective technique would be, for example, the following. And this is the projection error-based local ROM, which came because of some easy or interpretable reasons. And here I will try to explain why. If we use k-means for this example, let's say this v and u, and you have this lambda u. So you can see lambda u is nothing but a scale version of u. So you could actually represent this in with the same one-dimensional space. But if you use k-means, you will get something like this. So these will be clustered in the same one, even though they are orthogonal, and these will be separate. Probably based on this, they say, okay, probably we can use something like this idea to create a better clustering for model reduction. And please bear with me, I will just try to explain it, and this is quite easy. So you have S, which is your snapshot metric, in this case, these 4 points. First step, find the one with the largest number. Here it is, C1. And now project the rest of the points onto this. Okay, this is the projection error. And then find the largest projection error. Here it is. And I assign it C2. Is this projection error tolerable? Is within a tolerance? And here is something that you need to tweak. Okay, for each problem, this tolerance will be different. So you need to do a clustering with one tolerance, another with another tolerance, because you cannot tell, I want 5 clusters, I want 10 clusters, I want n clusters. You can tweak this tolerance. Okay, let's say for the sake of the argument that this is too large and I need to split somehow. And the way I split is like this. I will use the projection error again. So those snapshots that have a smaller projection error in this direction will be clustered together. And those who have a smaller projection error onto this direction will be clustered together. And I will repeat. I will repeat until this tolerance until I cannot split anymore, because everything is within the tolerance of bisection. For this particular set, let's say these 2 will be together, and these other 2 will be together. And then I effectively form this kind of binary tree structure. And then I would only do the singular value decomposition on the leaves of the binary tree. That's it. And this is the algorithm. Now it's very easy to understand. You got the snapshots, the bisection tolerance, and the tolerance of the SVD. So first, stage 1, as it says here, is create the bisection tree. Stage 2, compute the SVD. And then you get this structure. And this is an example of PVL versus k-means. For example, as you can see, k-means gives you these rounded clusters with their centroids. On the other hand, PVL gives you these kind of cones, as you can see. So the green one, for example, cross in the middle. This is centered data. This is random centered data. They cross in the middle. And well, this is just probably a better way of doing the clustering. There are many other ways to do it. For example, I'm showing here another alternative, which is the distance in the Grassmann manifold. So this is another approach that has been proposed by some group in Safran, and we are visualizing here using the multidimensional scaling. But basically, it's the distance in the Grassmann manifold. Or you can even choose another dissimilarity measure. Let's say I don't want to cluster on the snapshots, on the solutions, but on a quantity of interest. So they are similar because they have a similar quantity of interest, and I cluster them together. Well, that's the alternative, how to make the clusters. Now, online, how do you choose the best basis? Basically, well, I found 2 ways. One, either with the parameters, you get a mapping from the parameters, the parameter space to each of the bases, or you get a mapping from the solution to each one of the bases. Of course, you would not use U, but you will use the small representation, right? but you can pre-compute some operators, and then you can just monitor your small representation and then update the cluster. Some examples of this, for example, distance to the centroid in the parameter space. So you sampled your parameter space, and now if you have a different parameter, which is the closest centroid in the parameter space, and I use that, or which is the closest centroid in the solution space. So if you are monitoring your solution in the solution space. Well, that's the logical one. PBL has its own. I mean, if you have you check the projection on each one of the, basically you go down the binary tree, checking the projection error, and once you reach a leaf, you use that basis. That's one alternative. And another alternative, which is very interesting, is okay, I will train this either a classification neural network or a regression neural network. I will put the parameters, and I will get the optimal cluster. And then I will, whenever I get a new parameter, I will just use this to choose. Okay. Okay. There's something that I haven't mentioned, which is, well, I just said this, right? So you split it and do the SVD. It turns out that it's necessary to do some overlap. So you actually need to do some overlap and then do the SVD. Because, well, I will show you. Here is an example of a paper from CISA recently, from this year. So basically, it's using the k-means for doing the clustering, and it's using this centroid, distance to centroid in parameter space as choosing the basis. And as you can see, there are some jumps. This is some quantity of interest, and you are changing two parameters. There are two parameters being changed, and you get some quantity of interest. So if you put no overlapping, you get these jumps. If you add some overlap, then you get a more smooth response. And this is because you are monitoring the parameter space. On the other hand, you are monitoring the solution space. It might happen as something worse, that you don't even get to evolve to that solution. This is something that I did. Well, I just put the video. Basically, this over here is doing some overlap, which is not ideal. Let's say okay, let me explain. There are two sliders. One of them is applying a vertical force. The other one is applying a lateral force. What is going to happen is that, okay, now I push it all the way down, this structure, which is a plunger, and then I try to move it sideways. But it will not move because this cluster cannot evolve to this direction. If I follow the training trajectory, I can actually move there. But once I get back to this cluster, I get stuck. Because basically, I am evolving on the solution space, and this particular cluster is not rich enough. It cannot really go there. If I go to, I mean, this one has been overlapped, the same clustering, same 10 clusters, but it has a better overlap. Now you can really explore all the deformation states. So that's important, how to do the overlap, to do a correct overlap, in order not to overfit, let's say, the training trajectories. I don't know how I'm doing on time, because this is pretty much all that I want to talk about. If I have more time, I could probably talk a bit more about other things. Maybe I can answer some questions, but just wanted to give you some references. Okay, the Kratos repository is here. This is the hyperreduce for the model method that I showed. Some first papers on the method from a group in Stanford of Farhad, and some comparisons of these methods, clustering in the solution space, in the parameter space, in time, and also k-means versus PBL clustering, and some good reviews in other similarity measures. This is from the group in Safran. So I don't know if you have any questions, or I can continue.
Also, if online speakers have questions, they can unmute themselves.
Can I ask you, so when you were doing the three, so in your landscape, when you want to switch between the different you want to switch between different clusters. So imagine that there's something moving time, and as a sign password you want to switch between a cluster and another one, what do you have to do in the trivial instance or also in the parameter space?
In the parameter space.
No, sorry, in the solution space.
Okay, we have this parameter space, which is here. So basically, you input a new parameter and you measure the distance to the ones you already know. So
for the solution, for the reduced solution, it's so you don't have already the solution before. How do you know a priori which one will be the cluster, not knowing the solution or?
So you train your snapshot, right? So you already have your centroid in the solution space in Rn, let's say. You have the centroid there. And whenever you are in an initial state, you need to know your original cluster, where to start. And from there you can compute, let's say, the solution. Once you have the solution in that time step n+1, let's say, you measure which is the nearest centroid. If it's the same one, you keep in the same basis. If now the centroid is the one from the neighboring cluster, you switch to that one.
Okay, so you first compute the new solution and then
yeah,
the distance. But the distance is then computed on the full space of the solutions, or the distance. Because I mean, if you have different bases, so I'm talking about the solution phase. You have different bases, so I guess also the parameters, the Q of your function will be different in different clusters.
It is correct, yes. Yes.
So how can you compute the distance from, I mean, of Q with respect to the centroid of another cluster? You have to compute the full solution.
So there are some operators that are pre-computed in order to be able to use the reduced variable. This is one thing. Imagine that you have your full dimensional vector. If you have your full dimensional vector, then it's clear how to do it, right? Then the question is, how is it possible that you are updating only with the reduced variable? Well, I don't know if I can explain it right now, but basically you realize that there are some quantities that never change. So you pre-compute them, and then you multiply some operator with these updates, which is an increment in the reduced variable, and then you know what would your u be without having to compute your u. You know their distances, so you are updating the distances. You keep track of which is the distance to my nearest centroid in the solution space. Something like this.
Yeah, so you have like the change of basis.
The change of basis occurs, of course. Yeah, you don't have to do this necessarily, but I mean, you would have to if you want to really measure u at every time step. But the thing is, you don't need to. This is explained. I mean, probably I can explain it offline, but this is explained in this paper, the very first one from the method. So basically, this one, the first papers in the method in 2012 from the group of Farhad. So this is just just some linear algebra on how to keep track of the distances. But once you change, and I think this is something you mentioned, once you change the cluster, of course, your Q, let's say your first basis has 5 modes, the second basis has 15 modes. Then, of course, you need to change it. You need to then do this mapping. Yes, of course. You can also pre-compute this mapping, right? Yeah. So you don't need to really go there and then come back. You can use so that you can change your Q from 5 to 15 entries. That's it.
Are there other questions? But I have one just to be sure that I got it correctly. So there is a way to assign a cluster without coming back to the full dimension, right?
Yeah.
So, okay. And okay, and it's not using like classification algorithms, like for example, using neural networks that assign which parameter cluster.
Not necessarily. I mean, if you are just measuring the distance, I mean, the neural network is it's an option. But just using the distance, you can imagine that you're still in U. But since you can pre-compute some stuff, you don't need to be in U. You can be in the small dimensional, let's say, variables. But it's almost the same. It's the same, let's say.
And the other question was, I've tried also implementing something related to domain composition, so reduction, a local approximation both in the domain of the parameter space and in the spatial domain.
Yeah, I've not looked into that. I mean, in the Ramses, as I was mentioning the other day, in the Ramses, some methods were presented on clustering in the domain, and that's also interesting. And I was not very aware of that, but I mean, this method works globally in the domain, locally in the solution space. It would be an interesting thing to test. I'm not sure.